Hello, everybody. Welcome to my talk about crazy times and mad clocks. This is a story about rails, standards, and a proposal to standardize low latency digital clock distribution. Now, when you hear crazy times, maybe you think about the picture, The Persistence of Memory from Salvador Dali. What do we think about when we hear mad clocks? Well, MAD is an acronym that I created to refer to matched driver clocks. And you see a picture up there that we'll visit later in this talk. So it's almost Christmas. I'm in a very festive spirit. And here you can see me and a couple of friends on a little Christmas train. This picture was taken in Irvine Regional Park on December 14th. And there's a little story. We had done a mountain bike ride from Irvine Regional Park, and after the ride finished, three of my friends and I, we went through the park to the little entertainment village where children can do horseback riding or do little train rides. And so I was walking around there and took a picture of this train here. This talk is about rails, so this connected with me. The funny thing is, essentially, we kind of stumbled through this park, and then I end up behind this plywood wall with the three holes, and I don't even know what's in front of this. I'm just sticking my head through the middle hole, and I end up as the court jester here, the fool. And maybe some of my friends who worked at Broadcom in 2015 will remember me talking to them with a jester head. So somehow everything circles around in life. So this was a really funny moment now that I received this picture from a friend. Haven't staged it, it just happened like this. And now I'm weaving this into my presentation. Okay. Um, so everybody is talking about artificial intelligence, and so I'm going to use some artificial intelligence here in this presentation. And I'm also going to talk about CI, which is crazy intelligence, or maybe Christian's intelligence. And if you want to get in touch with me later, here's my email address, c.lütkemeyer@pixeda.com. And recently, my son asked me who his father was, and I asked him, well, why don't you ask ChatGPT? And so he asked ChatGPT, and the link above the AI box is the answer that ChatGPT provided. I'm pasting this now here on this page just for everybody. Maybe later you can take a look. I don't want to read it to you. It's actually probably better than I could have written it. So I'm glad ChatGPT provided this neat little summary. The only thing that was missing is that it didn't know that I had left Marvell in July to start my little company, PIX-EDA. And so that's an important change in my life, and I'm excited about this. And so I hope I can share some of my excitement and my know-how with you in this presentation. And maybe if you sit through this, you will think, wow, this is the craziest presentation that I have seen an engineer give in my whole life. And I hope it will at least be a little entertaining for you, but I think it may also be educating to you. So stay tuned. So on this slide, I want to talk about rail transport and timing standards. I'm not sure if you are familiar that ultimately railways were responsible that time got standardized. I guess faster modes of travel justified being more punctual in time. You couldn't just say the train leaves on November 14th, for example. No, you needed to have a good time. And before there was a standard time, 12 o'clock was essentially different from place to place, just the time when the sun was highest in the sky. So railways were essential to motivate the creation of the standard time. And so now I'm a chip designer, and when I have to work on a synchronous design, we have a clock signal, and the clock signal should be the same everywhere. So this is kind of like a clock standardization problem. And the distribution of these clocks actually is a very interesting engineering problem. And I want to propose here an implementation standard that can implement this in a very efficient way that makes life much easier for ASIC designers who have to distribute clocks with low latencies. So here is a summary of the clock rail standard proposal that I want to put forward. So this proposal will show universal geometry details and shielding of long-distance clock distribution rails with power mesh serving as a return path for digital ICs. We will use symmetric shielding with power and ground. We will use matched clock drivers, which are two-stage buffers with a stage gain of gamma equals to 10. Then for the foundries, it would be wonderful if they could plan these clock rails in their early process development and provide critical shared collateral to implement these structures. Recently, foundries are working on providing backside power, and in my thinking, we also need to provide backside clock. So that's really critical. And our EDA partners, they can then provide physical implementation tool support to implement these structures in our designs. Here is a picture of the important clock rail stakeholders that I see. At the foundation, there's really the foundry and the technology developers that develop the technology for us. Then there are the EDA houses who provide us with physical implementation tools. And then there's many different fabless semiconductor manufacturers. And in each of the larger fabless semi companies, you may have many different design teams. And each design team has its own resident clock distribution expert who implements clocks based on the best knowledge that they have. And we will later see there's sort of many different ways to implement these structures. And without a standard, there's many different schemes here. I want to essentially create a standard where instead of working in our separate bubbles, everybody kind of doing things that make sense for him without sort of seeing the big picture, where we can agree on one standard that makes life easier for everybody. And so then the foundry can provide technology for everybody. And this is a proven methodology, high quality, low insertion delay, no risks, and so forth. So I really like to get people to merge our bubbles into one standard so that everybody's life gets easier. I'm trying to make this talk entertaining, and so here is a beautiful picture of a peacock that I took myself a while back. And so I like to weave this peacock into my talk on the MAD clocks. And so this is one part of the crazy presentation here. I hope I can keep up your interest and you follow along. A technical presentation should have a solid structure like this bridge here. And I'm going to use this picture of this bridge to actually structure the outline of my talk. The first item, the introduction, the transport and timing standards, clock rail standard proposal, and stakeholders, we just did this. So we essentially traveled along this first section, and here are now the remaining items of this talk. I want to talk about AI and CI, CI being crazy intelligence, AI artificial intelligence. I want to talk about the history of the railway standard, the history of my clock distribution work that I have done in the past, the complexity of the clock rail design space, transmission line theory and pulse propagation, skin effect and wire lithography, fear and greed versus holistic optimization examples, the MAD buffer and clock distribution topologies, MAD clock collateral that the foundry could provide, then the topic of backside power and MAD clocks, and then finally the proposal of the PIX-EDA MAD clocks. So now we are going to dive into the artificial intelligence versus crazy intelligence topic. I just want to mention a brief appreciation of artificial intelligence. The picture that I use for my agenda is essentially an AI processed image of a low resolution picture that you see here. So yeah, there's some amazing stuff possible with these tools. Everybody's talking about artificial intelligence these days, and the picture on the left was from LinkedIn, the AI hype. What is real? Now, I want to contrast this a little bit to the crazy intelligence. And crazy intelligence is what I think some human beings are applying. And so when I'm riding around on my bicycle through my community, I'm exposed essentially to lots of different things. And I'm thinking about all kinds of things, my engineering work, what I see. I'm thinking about my family. I'm thinking about things that I love. And I think about interesting pictures that I've taken. I may think about my passions and the truth, what is real in life. I also may think about things that I hate, and that hate may motivate me. And in this case, you see already, I had the doggy bag, and I got that and picked up what I saw there on the street to leave the neighborhood in a better state than I found it. So that's crazy intelligence at work. If we now go back to artificial intelligence, I think what is really missing there is love, passion, truth, humor, pain, fear, greed, hate. Um, Maybe it can fake the behavior of lots of these human emotions, but I think human beings are much, much more complex in how we experience life. Um, Ultimately we all will die. The AI will probably be upgraded at some point. That's a different process. And so I'm thinking about these things. I find this a very interesting world and time that we are living in these days. I like to share a specific example how sort of what I do in my personal life then kind of gets reflected in my professional life. So here's an example what I love. I was visiting my mom in Germany this September, and we were lucky in the bakery. There was one last piece of Black Forest cherry cake, which we love, and this was like 1.8 pieces, not quite two. And the bakery was kind enough to sell us this piece at the price of one piece. So this was a quantization error in our favor, and we truly enjoyed this special piece of cake. If you have been following me on LinkedIn, you may remember I posted a piece here, Chip Interconnect Reality versus Model. And here I had created this piece of Black Forest cherry cake and created an acronym, CREAM, for a technology that I find very valuable. CREAM is capacitance, ratio, extraction, and measurement. And this goes back to some work that I did at Broadcom in 2015 and presented at the 2016 Tau workshop. This technology essentially allows to measure capacitance ratios in the metal stack and then identify issues in manufacturing. Today, manufacturing measures resistance on metal layers, but that tells you only about the cross-section, not about the spacing, for example, to the layers above and below. So if this CREAM technology was adopted by manufacturers, then we would get much more data about potential outlier situations in the manufactured metal layers. So here the connection essentially me and my mom eating the Black Forest cherry cake and my brain ultimately sort of seeing this analogy that the cake and the metal layers have this beautiful layering and then the cream can be transformed in this kind of acronym. I'm not sure this can fall out of artificial intelligence because the artificial intelligence will probably not eat any Black Forest cherry cake. And so, how can it experience the things that I'm experiencing that create these interesting analogies? So now we are going to go to history of the railway standard. If you look at the origin of the railway standard, you will find that hooves and wheels don't track well. This is a map that shows the roads of the Roman Empire. And the Romans, they built all these roads to project power to places far away. And they used these wagons. You can see one here. It actually has some suspension with some leather straps. This is from a museum in Germany. And then later you find similar wagons when the pioneers were moving westwards in the United States. Then later on, there were essentially rails in cities. Here's an example from New York. And so these rails had a standard gauge, 4 feet, 8.5 inches. It's an odd number, but this number essentially traces back to the Roman wagons. These wagons, they used to make essentially lines on the road. And once you had lines at a certain distance, if any wagon maker made wagons where the wheel separation was different, that wagon wouldn't roll so well anymore. And so the wheels are separate by about the width of 2 horses. So it's kind of the double width of the railway. And we can go forward here. Germany has a leaning train in corners. Essentially, it leans in so that the passengers don't feel the centrifugal forces pushing them to the side. And this is essentially still the same rail width that the Roman wagons had. So it's kind of an interesting historic background how these widths of the rails came about, and it has been a standard in place for essentially millions, thousands of years. I like to give you a short summary of my clock distribution work. I started to work on this topic of low insertion delay clock distribution when I was leader at the Timing Sign-Off Center of Excellence in Broadcom. And so this is work that was done at the 40 nanometer node, quite historic if we look at recent technologies. And at that time, the designers who were making reticle-sized chips were complaining that the derating margin on the clock insertion delay was essentially eating up maybe 80% of their usable cycle time. And so they were in a position where sort of a nominal 1 gigahertz design had only sort of 200 picoseconds of usable cycle time because the early late derates on clock insertion delay was just killing them. And so they were essentially asking for margin relief, and that made me very uncomfortable. And so I started to think about if I can come up with a technology that massively reduces the clock insertion delays, then I can keep my margin and my good night's sleep, and we are all going to be probably more likely to be successful here. So I started these comprehensive simulation sweeps where I looked at different widths and spacings of traces. I investigated different lengths, driver sizes, inverters, buffers with 2 stages, 4 stages, different buffer stage gains, looked at different distribution topologies, and also at the insertion delay timing error when we looked at these traces as the RC model or an RLC model that is more aligned with reality. So I found technology that can reduce the insertion delay by a factor of 8, and that's really like a game changer at that point. And I have deployed this kind of technology heavily in more recent coherent DSP SoCs in FinFET technologies that I have been working on. I like to give you now a visual impression of the complexity of the clock rail design space. I like you to take a look at this picture of a peacock, and I like you to think about how this peacock has been optimized by evolution for a particular environment and space. And then think about this is a bird, and this bird has a very long tail with these striking patterns. And if an engineer had to design a bird, he would probably never come up with a peacock because this bird can't even fly. So this is a very exceptional animal, but it's very successful. And so I like to take this picture to now go through the complexities that are involved when we try to build low insertion delay clocks. So there are questions of lithography, like the rail width that we choose, the rail spacing that we choose. There's going to be a power mesh that is adjacent to those rails. The driver size is a parameter that has to be evaluated carefully. The topic of power is very important. And first, there is the power of the driver itself. Then the clock rail may have different capacitance values that influence the power. But then the power of the whole design will improve significantly if we can cut down on the insertion delays, because then there is more useful cycle time for the design. Then there is the question of delay, driver delay, and the delay on the rail itself. Are the transition times acceptable? That's an important topic. And then the jitter in the design. If we have less delay, then there's going to be improvements to clock jitter. Then we have the topic of RLC reality, timing modeling. STA timing, unfortunately, only uses RC models. It doesn't know anything about inductance. So that's a concern. We need to understand how the ideal transmission line model, which is an LC model, behaves. we can use SPICE to compare timing between LC and RLC models. Some designers annotate SPICE timing from clocks into their STA designs. There's all kinds of things being done to deal with low insertion delay clocks. One very important aspect is the skin effect. We will look at this later. And then the topic of power integrity. There is a connection in designing these drivers that can improve or improve power integrity or make it worse. And then there's even a reliability concern that comes into the picture when we develop these drivers. Now, one aspect that I really enjoy about the Peacock is that it is deploying binary signaling in a very powerful way. Here you can see essentially the logic 0 of the Peacock signal, and here is the logic 1. So it's quite impressive if you are standing in front of a bird like that. Really beautiful. Unfortunately, when I met this bird, he was in a Faraday cage, and so that kind of took away some of his beauty. I could only take these nice pictures by kind of putting my camera lens into one of these mesh openings. But thinking about this and relating this to AI, can AI feel the kind of sadness that I experienced when I was looking at this beautiful animal essentially in a cage? We are now moving forward to transmission line theory and pulse propagation. So the structure that we are thinking about here is a thick top metal clock transmission rail. On the left side, you see a matched driver. Here it has an impedance of 50 ohm that is matched to the transmission line impedance of 50 ohms for the clock rail. Here in the cutout, you see the cross-section of an advanced semiconductor metal stack where you see the thick top metal, which is most useful for long distance clock distribution because it provides the lowest resistance. The driver shoots a transition over this transmission line to the receiver, and our goal is to minimize the total delay of driver plus transmission delay. Those of you who follow me on LinkedIn may remember my recent post about a mountain bike ride along the Impossible Railway in Anza Borrego State Park. So the standardized clock rails would be similar to the railroad tracks with a certain distance and geometry. And this would be essentially a target that all the designers could have and share. Some of you may know that my daughter plays on the UCLA tennis team, and she had some recent successes there and received some recognition. And I started to think, is there something that I can use here for my presentation on the clock signal distribution? And I thought maybe the tennis ball is a very good analogy to think about the electromagnetic wave soliton propagation. The soliton is essentially this sort of interconnected electric and magnetic field that is pushing forward at the speed of light. And so if you want to sort of take a look here, as the tennis ball is flying forward, that's how a transition on a transmission line can move forward. And so I'm going to use this concept of a soliton shaped like a tennis ball to kind of give you a better impression how pulses travel on a transmission line. We can think about a transmission line, an ideal transmission line, composed of very short sections with inductance and capacitance to ground that are connected with each other. And then we have the driver shooting this transition over this ladder structure of L's and C's, and it will then arrive at the receiver. When we want to understand what happens with these linked inductive and capacitive elements, we can look at each section. There's a current I1 going in, a current I2 coming out, and then there's a current flowing into the capacitance. We have a voltage V1 coming in. There is a inductive voltage drop over the inductor. Delta V1 equals delta L times di1 over dt. And then we have the voltage on the capacitor, which is created by integrating the current I3 onto this capacitance. So this creates a second order differential equation in space and time, and the solution of this equation are electromagnetic waves that are traveling forward or backward. You can think of this kind of like the electrical field and the magnetic field being interconnected like a yin-yang and propelling each other forward, kind of like a spinning wheel or this flying ball. On this slide, I like to give you a visual impression of the impulse propagation that occurs on the transmission line. So the driver creates a current VDD over 2Z0 that creates a transition. This transition then propagates at the voltage of VDD over 2 to the end of the line. At the end of the line, there's an open-end reflection. So then there is a wave traveling backwards, equal in amplitude VDD over 2, which then overall gets the line charged equal to the supply voltage. And at that point, essentially everything is settled out. So it takes one round trip delay when the driver is matched to the transmission line, one round trip delay to settle the voltage to the final value. Here I like to show you a way to calculate the pulse delay tau TL on a matched driver transmission line. We can start out from the current of the driver. That driver current is equal to VDD over R driver plus Z0. And for the matched driver, this is VDD over 2Z0. You notice that increasing the line impedance is useful in reducing the driver current. We can then look at the charge on the line when the forward traveling VDD over 2H hits the open end. At that point, the driver has provided the charge Q forward equals to C line times VDD over 2, which is equal to the driver current times the tau TL transmission propagation delay. The product of these two is then VDD over 2Z0 times tau TL. You see the common terms here. We can eliminate those and then simplify this equation to tau TL is equal to Z0 times C line. And you may notice that this is very similar to the time constant of an RC element. And this is already an indication that by proper sizing the driver, we may find a solution where RC modeling of a transmission line essentially gives us sort of a very good approximation of the true RLC model of a transmission line. Here, a specific example, if we have a transmission line with a line impedance of 50 ohms and the wire has a capacitance of about 0.3 picofarads per millimeter, then we get a propagation delay of 15 picosecond per millimeter. And so looking at these 15 picoseconds, if you do chip design in advanced technologies, you know that fast gates do have delays in this order of magnitude. And that's why we need to look at these transmission lines really as a pulse propagation problem and not a frequency problem. Next, I like to talk about skin effect and wire lithography. Here you see now our clock rail between two return path VSS rails. Between the conductors, we find our electromagnetic wave solitons. And the skin effect essentially is an effect where the current only flows directly under the surface next to the electromagnetic wave. The field essentially doesn't penetrate deep into the conductor. The depth of penetration is a function of frequency. You can find online skin depth calculators for 100 gigahertz frequency component. You get a depth of 0.2 micrometers. At 10 gigahertz, it's 0.65 micrometers. The dimensions of the conductors on the thick top metal are about in the range of 1 micrometer. The line impedance is square root out of inductance divided by capacitance. And so when we look at this equation, we can see when we reduce the capacitance, then the line impedance increases and then the driver current will be lower and we will ultimately have less resistive loss on the trace if we can get the line impedance increased. So that's an important optimization opportunity. Overall, we have to remember now the current crowds on the conductor surface, and that means that wider rails do not reduce the high frequency resistance. If we stretch our clock rail wider, we are just adding additional capacitance to the top and bottom, but the current is still going to just flow on the left and right edge of the conductor. Wire lithography is an important aspect that we need to understand. Dense wiring on integrated circuits has a width to spacing ratio of 1 to 1. The aspect ratio of height over width is 2 to 1. We also see that the wires are wider at the top versus at the bottom. This effect is quite pronounced here in this picture. When this is being manufactured, then there can be variability on these edges from etching, and the situation that the spacing is less at the top ultimately creates a stronger electric field at the top, and that means that the currents in the conductors are also crowding towards the top of the conductor. Here is now a little mock-up picture. If we created traces that are double minimum width and double minimum spaced, then the variability of lithography is essentially reduced in relative terms. So we have reduced sensitivity of electrical parameters to the lithography changes here. Also, by spacing the conductors wider, we end up with less capacitance. So this is beneficial because then the line impedance is higher and the currents are lower. We are going to review now a fear and greed versus holistic optimization example. Let's have a look at the fear and greed RC optimization example. We start out with a minimum space solution, and our designer may know that inductance exists, so he has to use VSS shielding. And because tools don't model inductance, then he commits to use minimum spacing to the neighbors, which minimizes the inductive effect. Now, our designer may be unaware of the skin effect, and so this is kind of the icing of ignorance in this problem. He may choose to minimize the RC delay very aggressively, and this can be done by applying a very, very low resistive driver at the entry of the transmission line, and then he may even choose to taper the wire, so make it more narrow towards the end of the line to reduce the capacitance. And in that case, we may actually reach a point where the RC model propagation speed on the trace exceeds the speed of light. And so this is something where Albert Einstein probably starts to spin in his grave. So this is not a good optimization point. Here is now the holistic match driver RLC optimization. So here our trace is now double width, and the spacing is also double width, which essentially creates these kind of square-shaped areas for the electromagnetic field between the conductors. So at this point, we have embraced an increase in inductance, which provides us this relaxed lithographic sweet spot, double width, double spaced. We acknowledge the existence of the skin effect and refrain from widening the clock trace, because widening the trace is not going to help us. The resistance is only determined by the area where the skin effect lets the current flow. We choose to leverage the power mesh as a return pass. So there's a symmetry. On the left side is VDD, on the right side is VSS. And these aspects essentially create a picture where our driver is smaller, we have lower power. Also, the area of the whole structure is now less than in the fear and greed scheme. This structure actually provides a small RC versus RLC delay error. So with this structure and a matched driver, we can actually rely on SDA for timing analysis. And then there is a cancellation effect of noise because we are coupling both from VDD and VSS into the clock rail, and this eliminates the first harmonics of the driver. Here I like to show you a picture why VDD and VSS shielding is a sweet spot for MAD clock rails. If you look at the supply noise of CMOS circuits, then the noise between VDD and VSS is out of phase. So they're essentially moving in opposite directions. And so if we now put our clock rail between VDD and VSS, then the noise is canceling each other. And so by using VDD and VSS shielding, we get beneficial supply noise cancellation where we have less jitter. On this slide, I like to show how we have a power integrity gain from VDD plus VSS shielding. In 2017, I presented this slide at the Tau workshop and essentially explained how VDD and VSS shielding breaks the demand current of the driver into two bumps at the rising and falling edge of the clock signal, where if we had lumped VSS loading on the driver, we would have a large demand current at the rising output and a very small demand current at the falling output. So breaking coupling into VSS and VDD essentially eliminates the first order harmonic of the demand current of the clock driver. So this is a substantial benefit. In the holistic MAD RSC optimization, we will also restrict the distribution topologies to known good structures like point-to-point, center-driven T, balanced H, spine, and ribs. And we will also use a match driver to the line impedance Z0 and the chosen distribution topology. And with these measures, we avoid surprises from random crow feed structures or asymmetric branches, and we also have no overshoot at the end of the line and ensure there's a small RC versus RLC delay error. This slide shows how we can find this engineering sweet spot for the MAD rails by comparing essentially these structures with different dimensions to the minimum width, minimum space reference point here in the table. Minimum space and minimum width provides the smallest area, has the largest resistance, smallest inductance, and most of the capacitance is to the neighbors on the return path. We can then choose to increase the width of our trays. At that point, the resistance will be decreased, the capacitance will increase. We can then go down the greedy optimization path and make very wide traces where in an RC model it appears as if the resistance is going down substantially, but the capacitance coupling to the top and bottom is growing substantially. We may get this false exceeding of speed of light point here. Then we have our double width, double spaced sweet spot where resistance is lower, capacitance is lower, and inductance is higher than in the minimum spaced point, which helps us to use a smaller driver, and we will end up with lower power and less resistive loss. Now, you could start to pull the traces apart even further. However, at this point, now you occupy more space, and the modeling error between RC and RLC model is increasing. Also, more of the field is coupling to the top and bottom, which are not so well defined, depending on what layout densities do we have. So that's not necessarily beneficial. We are now moving forward to the MAD buffer and clock distribution topologies. On this slide, I like to explain the design principles for the two-stage MAD buffer with a gamma of 10. Typical standard cell CMOS buffers use a gamma ratio of 3 or 4, which means the second stage is about 3 or 4 times as wide as the input inverter. This leads to minimum insertion delay. The MAD buffer will be built with a gamma of 10, and that provides a small increase in buffer delay from the first stage to the output inverters, but it ensures that there's a small sum of RIPS buffer input capacitance in a spine and RIPS structure, and it also moderates the output transition time somewhat versus gamma equal 4. The output connection from the MOSFETs at the silicon active level to the top level metal has to be built with a stacked via manifold, and we need to essentially get the matched driver resistance at the point where we hit the top level metal. So the via resistance is part of our MAD. And in today's technologies, the stacked via may have to be constructed individually for each instance, because we have shifting metal pitches on different metal layers. And so this is a back-end tool problem, how to connect the buffers once they are placed to the locations where the power rails are. The inverter from the standard cell library that is being deployed here needs to be chosen so that the output resistance of this driver ultimately leads to the correct matching driver impedance. Here I like to show you a brief animation why it is important to not overdrive the line. Overdriving the line happens when our driver resistance is much smaller than the matched driver resistance or line impedance. So we see that the current that is pushed out by the driver is VDD over R driver plus Z0. And when R driver is small, this creates essentially a voltage VDD times Z0 over R driver plus Z0, which can approach VDD. And then when we have the reflection at the end of line, then the voltage may overshoot to a level of VDD times 2Z0 over R driver plus Z0. And that means for about the round trip time of this line, the soliton overshoots, creates a voltage beyond VDD, which could create gate oxide reliability concerns. And it also now takes more time for the line to actually settle to the final value of VDD, because we have sort of this now overshoot, undershoot, bouncing back and forth several times. So it takes more time to settle. Here I like to give you the table of the different MAD clock distribution topologies that are beneficial. It starts with a point-to-point connection where the MAD driver resistance is equal to the line impedance. We can have center-driven traces with impedance Z0 over 2. A bottom-driven T also needs to use a driver of Z0 over 2. A center-driven balanced H structure needs a driver with Z0 over 4. And then the spine and RIPS topology has an impedance of Z0 for the spine, and then Z0 over 2 for the RIPS. And the RIP drivers will be connected every 150 to 200 micrometers to the spine. And then we can use multi-source clock trees connected to every 150 to 200 micrometers on the spines. It's critical to have the driver via stacked resistance significantly smaller than the MAD driver resistance. And we don't want to overdrive the wire to avoid the overshoot. If we follow these principles, then the MAD RLC timing is very close to the RC SDA model. And for these structures, we can ignore the transition time violations in sign-off. The RC model transition times appear essentially larger than what is happening in reality there. And since this is at the origin of the clock tree, the transition times are really not that critical in this context. I want to now briefly review the MAD clock collateral. The question that I'm asking myself here is, can the foundries and EDA vendors provide comprehensive MAD clock rail collateral? This would start with clock rail layers and dimensions for the double-spaced topologies, the standardization of top-level power mesh with the VDD clock BSS rail slots. Here, it's important that the power mesh dimensions are related to the metal pitches of all layers. There's a smallest common multiplier problem here. The solution must maintain the metal density rules below the upper limit. We need the multi-row MAD driver cell layouts, and they should be compatible with standard cell dimensions. We need to provide the trace topologies and the maximum lengths. It has to be ensured that the design meets the antenna rules, so there's no damage from charge collection during manufacturing, and the EDA solution providers need to provide automated routing and via manifold creation on the fly. Now we are moving forward to a new and exciting technology, backside power, and how MAD clocks need to be included in this work. The power density of integrated circuits has gotten so large that the foundry is now starting to think about providing miracles where essentially the power delivery structures are produced on the backside of the wafer. So the wafer is being thinned, and then the thick metal structures for power delivery are built on the backside. Now, with respect to clock distribution, it now becomes really important that these clock rails can coexist with the power delivery structures. And so it would be wonderful if the technology providers in the foundry take this into consideration as they're developing the backside power technology. We are reaching the final destination of our talk. We are back at our complex design space picture here with a peacock. We looked at many of our parameters, and we can now specify what do MAD clocks entail. This is essentially an engineering sweet spot. On the lithography axis, we are going to use a rail width that is twice the minimum width. This works for lengths of about 3.5 millimeters if metal is 1 micrometer thick. We will use double minimum spacing. We will use power mesh with VDD and VSS shielding. We will use matched two-stage drivers. The matching has to take into account the Z0 of the trace and the topology that we choose. We will get significant power reduction for the driver, the clock rail, and the design. We get massive reduction in insertion delay compared to standard CDS. There will be good transition times of these signals, and the jitter will be much reduced. We can use SDA timing with an RC model the RLC reality and spice and the skin effect don't even have to be considered anymore because we are following these design principles. So this is covered by the small RC versus RLC error of the MAD clock scheme. The power integrity is improved because of VDD and VSS shielding and because our drivers now use less power, so the total current that the clock delivery system here needs is reduced. And then we also avoid any reliability risks from overdriving traces that could create overshoot problems. So here a final summary on MAD clocks and their benefits. They provide a safe design kit for low latency digital clock distribution. They allow us to ignore inductance consciously. A standardized comprehensive foundry support could save significant work for fabless customers. And then the EDA providers could provide a unified support for customers who are adopting the scheme. So there's also less work on the EDA backend support side. I hope this proposal will reach our foundry and EDA stakeholders and they will think about this. There's an opportunity here to adopt an engineering sweet spot that can make the life of the clock designers in the fabless world significantly easier. Thank you for listening to this presentation.